Hello viewers, welcome to Gurukul Live Lectures. Myself Dr. Preeti from Department of Computer Science, Aryabhatta College, University of Delhi. My topic for today is searching and sorting techniques which are very important in data structure. So the agenda for today's lecture will be, first we will see what is a searching problem is, what are the common techniques available for searching which are linear search and binary search. Then we will go through some sorting problems and its various techniques like bubble sort, insertion sort and selection sort. Coming to searching techniques, let's try to understand what do you mean by searching technique at a glance. So that is process of finding a given value position in a list of values. So basically we are given a key element or a particular element, and that we need to look upon and that we need to find upon in a particular list of values. Now if that particular item, if that particular search key is available within that list, that we need to decide whether it is available or not. If it is available, we will be returning the position that which particular position it is available, and if it is not available, then a flag or -1 or something of that sort indicating that it is not available, a value will be returned. So it is about deciding whether a search key or an item is present in the given data or not. What will be the various searching techniques? These are sequential search, binary search, jump search, interpolation search and Fibonacci search. But if we consider only arrays as a data structure, we can say only sequential search or binary search are the most commonly used techniques, while these Fibonacci search and jump search are for the other commonly used for other kind of data structure. So now again, searching can be of two types on the basis of their categories. It can be internal searching or it could be external searching. So internal searching is when it is performed inside random access memory or inside memory, that is internal searching, and when the data structure on which searching is performed is available in the external memory like hard disk and so on, that searching is known as external searching. So in order to search an element in a given array, it can be normally or generally done in following ways. One is sequential search and another one is binary search. Let's take a deep look on them by one. Coming to sequential search, it is also known as linear search. In this linear search, it starts at the beginning of the list and checks every element of the list. This is one of the most basic and simple search algorithm. So the idea is we need to search a particular element. Now as you can see on the screen, I am having an array of values, data values in which are 10, 5, 15, 20, 25 and 35, and if I want to search a particular element, I will start from the first number which is 10, and then I will match the number which is my key value. So key value, that is the number which is to be searched, is already given to me. I will be matching the first element in the array to the key value, whether it is equals to this. If it is equals, if they both are same, that means the first element in the array and the element which I am looking upon, which I am looking for, are the same. I will just return the position on which position it is available, and I will break the search and then come out. So basically what we are targeting is actually looking upon the first occurrence of the data value or the search key. So one by one it will compare the element to be searched, which is our key value, with all other elements given in the list. Now if element is matched, it returns the value index, else it returns -1. So it searches an element or value from an array till the desired element is found, or till the end of the array or the end of the list. If it is not found, it searches in a sequential order on a particular sequence. So that's why this is known as sequential search. Now coming to the application areas where it is used most commonly. So, it is ideal for an unsorted or unordered list which is not following any particular order among its data values. And when there are fewer elements in a list, this type of searching is perfectly fine, because if there are more than a particular value, or if we can say if there are too many values or the list is too large, this type of sorting techniques becomes very costly in terms of time efficiency. So, it is suitable for a list in which number of elements are less, or it is suitable for a list which is for fewer elements, and there is no condition upon in which there is no condition on the data values. That means it is not a necessary condition to have data values in a particular order or sorted values. So, it is ideal for unsorted or unordered list. Now, as I have already told you that this is a very simple idea, or this is the simplest most search available. So, for each item in the list, so in order to go about this particular implementation of linear search, we will look for what? For each item in the list, if the item or the search key value or match items which you are looking for is equals to value present at the first position, we will return the location, else we will keep on checking, else we will keep on going till the last value is found. And if we find the value in between, we will return the index of the array or position on which it is available, and then we will end the procedure. Now, sequential search is very simple. Starting from first to last element, it will keep on matching the desired value with each and every element. Now, coming to the next kind of search is binary search. Now, binary search, the important condition with binary search is it can be done for sorted arrays only. If your array is unsorted, if the data values are not stored in the sorted order, you cannot perform binary search. It is working on the principle of divide and conquer. It will look for a particular element. The strategy will be the following. It will compare the middlemost element of the array or middlemost element of the collection, and then it will decide that whether to look upon in the first half or whether to look upon in the second half if your element is not equals to mid element. Now, to understand this, what actually is happening here? So, first of all, we will find out the mid element in the array, and the item or the key value which is to be compared will be matched with the mid element. If the mid element is the value which we are looking upon or which we are searching, we are done here, and then we will return the index. Fine. Now, but if mid value is not the value which we are looking for, then we need to decide that whether value which we are looking for is less than mid element or it is greater than mid element. If it is less than mid element, then we look in the first half of the array because our list is sorted, and if it is not, that means the value which we are looking upon our item is greater than the mid element, we will look for the element next in the next step only in the right half of the array. So, in this way we are taking advantage of, as we have told that array should be sorted. The sorted array is giving us the advantage that every time we are dividing the array in half. In half means we are taking the first half or we are taking the second half if the element is not found at the mid, and this particular idea we will be repeating either with the first half or with the second half. Okay. So, now essentially we are doing what? We are comparing the key element with the element in the middle of the list or the array. If a match is found, we will return the index of the middle element and we are done. If not, then we will check whether the key element is less than or greater than the middle element. If the key element is greater than the middle element, we will pick or we will work on the elements on the right side of the middle element, and if the key element is lesser in value than the middle element, then we will work on the left side of the array or left side of the middle element, and then we will start again from step number 1. So, step number 1 says taking out the middle. So, that next middle will be taken out either in the first half or in the second half. So, here let us say we are looking for an element which is 23 and the middle element is 13. Now, we can easily say that 23 which we are looking for is more than this 13. So, that means we need to discard the first half of the array and we will be looking our element as it is greater than the mid element, we will be looking that particular element in the right side of the array. So, in coming to the right side of the array, what will be the changes? We will be taking our first element or the first value as the mid plus 1 and the last element will be taken as it is. So, now our new array will start from mid plus 1 to the last element, and if we would have taken the first half or the first part, our last element would have been the middle minus 1 element which is 8. So, we would have looked for the element in the array from 1 to 8. So, either we will shift our first element or we will shift our last element depending upon in which array, in which part of the array we are looking for that particular element. So, coming to the pseudo code, we say that low is 0 and high is n minus 1. So, low is 0, that means we are starting from the 0th index and we will be going to n minus 1. And what we need to do? We need to pick the mid element and then we will see whichever array part we will be going on till when low is less than equals to high. We will find out the mid, and what is the strategy to find out the mid? Mid will be found out by low plus high divided by 2, that means middle index we are taking upon. Then if the mid element is greater than the value, that means we need to look for the array in the first half. So, our high which is the last index will becomes mid minus 1. So, now our new array in the focus will be 0 to mid minus 1. Else, if this is not the case, the case is a mid is less than value where a is the array, that means mid element is less than the value which we are looking upon. We will say low is equals to mid plus 1. Low is equals to mid plus 1 gives us the right half of the array starting from mid plus 1 to the last n minus 1 high index. So, either we will be changing our high index as mid minus 1 if we need to look upon the element into the first half, or we need to or we will be changing our low as mid plus 1 if we need to look upon the array in the right half, else we will be returning mid. So, there can be 3 cases, either we will be looking for in the element in the first half, or we will be finding it onto the middle element itself, or we will be taking it in the right half of the array. And this we will keep on doing. This is an iterative procedure. This will keep on doing till low is less than equals to high. So, low is less than equals to high is actually shrinking the array every time by a factor of 2. So, that is why we are saying that binary search is working on the principle of divide and conquer. So, binary search every time is dividing the array into the half, that is every time it is dividing the array by a factor of 2. So, ultimately we will be finding our element at the position mid. So, if we are finding the position element at the mid in the first iteration, well and good. If we are not finding the element at the mid in the first iteration, we will look for that in the either the left half or in the right half, and we will repeat the procedure. In the left half we will find the mid, check the element, and then again we will keep on dividing it every time by 2, and this will go on while low is less than equals to high. And after all the procedure, if it is not finding the value, we will say not found. So, this could be another condition, that the index is that means your key item is not available, then we need to return not found. And if your item is available, we are going to find it in one or the another iteration onto the mid element itself. So, binary search, but the condition with the binary search is, as we are just discarding the one part of the array, either the first half or the second half we are discarding and taking the another part into consideration, the elements must be in sorted order. If elements are not available in sorted order, you can't perform the binary search. But if elements are in sorted order, this is one of the most efficient search techniques which are available in data structures. Now, coming to the second thing, which is sorting techniques. Now, what do you mean by sorting techniques? Sorting is nothing but putting the elements of a list in a certain order, in a particular order, whether in an alphabetical order, in increasing order according to their numeral value, or in the decreasing order according to their numeral value. Whatever the order is, if we want to put elements of a list in a particular order, this process is known as sorting. But output of any sorting technique or output of any sorting algorithm must satisfy, generally we do it in the increasing order, it could be in the decreasing order. Another condition is what actually an output of the array or what actually an output of the sorting technique is. It is actually a permutation of the input. So, how can we say that it is permutation of the input? It is just in reordering or it is just in rearrangement, and we need to retain all the original elements. So, let us say we are having elements A1 to A10, 10 elements are available, and then these are jumbled in the sense these are not in a particular order, and then we have performed a sorting procedure on that particular list, and we have arranged these A1 to N A10 numbers in a particular order, increasing or non-increasing, whatever is the requirement of the application or whatever is the requirement of the user is. So, what actually this output is? This is just an rearrangement, this is just an reordering. So, simply we can say the output is just a permutation, and we need to retain all the original elements. Any original element must not be missed from the output. So, it is just an rearrangement, reordering or permutation, different permutation of your input. What all could be the characteristics of a sorting technique? So, generally a sorting technique is identified or characterized by its computational complexity. So, computational complexity is how much time with respect to input size it is taking, whether it is taking order n log n, or whether it is taking order n square, or whether it is taking order n. Whatever the computational complexity is, this is the main characteristics of a particular sorting order. Then what about memory usage? Memory usage can be defined by the term in place, whether your sorting technique is in place or not. So, in place sorting technique does not need an extra amount of memory or does not need much extra amount of the memory, does not need extra amount of the memory more than a particular limit. That kind of sorting technique is known as in place sorting technique. So, whether the sorting technique is in place or not, that is also a kind of important characteristics. If the memory, if the sorting technique is not in place, that means it is requiring for a lot of extra memory while performing the procedure. And if it is in place, then it will take a certain limited amount of memory extra for performing the swapping or for performing the reordering or rearrangements. So, memory usage is defined by the term in place. Another characteristics which is very important in some sorting technique, for some sorting techniques or for some application where sorting techniques is used, is stability. Stability is defined by, or stability can be understood by, let us say we are having one array of elements 1, 2, 2, 3 and 4, or 1, 2, 2, 4 and 3. Now, if we are going to arrange this array into 1, 2, 2, 3 and 4, whether the 2 at the index 1 in the input array will be placed as index 1 or will it be shifted to index 2 in the output array. What I am trying to say is, if there are two elements occurring back to each other or occurring in a particular order in the input array, whether they will occur in that particular order in the output array also. If this is the case, that order has not been disturbed for the same values, that means your sorting techniques is stable, otherwise your sorting techniques is not stable. So, summarizing the characteristics, it comes to computational complexity, very important, then whether it is an in place technique or not, and whether it is an stable technique or not. Coming to types of sorting algorithms. If we want to categorize the sorting algorithms, they can be categorized on the basis of techniques. Obviously, computational complexity is also a way to categorize the sorting algorithms, but if we want to categorize the algorithms on the basis of techniques, we have two categories. One is comparison based, another one is non-comparison based. So, comparison based technique says, in order to rearrange the elements, in order to give the output, the elements will be compared with one another. Let us say array is A, and if we are saying we are having two elements, A of I and A of I plus 1 or A of I plus let us say K, where K is less than N obviously. So, we will be comparing the element A I and A of K, and then we will deciding whichever to put where, in the increasing order or in the decreasing order, at the first position or at the last position. So, the position will be decided on the basis of comparison. If there is no comparison between the elements, and then without comparison we are sorting the array or sorting the list into a particular order, that kind of technique is non-comparison based. Yes, non-comparison based could be a technique where you do not need to compare, or where there is no comparison involved between the individual elements. There is no less than greater than sign in your pseudocode or in your programming, but still you will be able to generate the right output of the sorting technique. So, comparison based are very which techniques are comparison based techniques? You have a bubble sort, you have shell sort, insertion sort, selection sort, merge sort, quick sort. All these common sorting techniques, or even heap sort, all these common sorting techniques are comparison based. And if we are talking about non-comparison based, there are limited examples like counting sort, bucket sort, radix sort. All these techniques are non-comparison based technique. So, in today we are covering only some of the comparison based techniques. First of them is bubble sort. So, as I have already told you, we are covering or we are focusing on the comparison based techniques. Bubble sort is a comparison based techniques. It is also known as sinking sort. Now, what is the strategy? What it does? It compares adjacent elements and swap them if they are in the wrong order. So, let us say we want to arrange the list into the increasing order. It will compare the element at the first position and the second position and then swaps them if the second position, if the element at the second position is lesser than the first position, if the lesser than the element at the first position, then it will swap. So, if the order is wrong according to the output required, it will swap the element, and this will be repeated until the whole list is sorted. Now, why this is known as bubble sort? Because a smaller or larger element, depending upon you compare greater than or less than strategy, a smaller or the largest element bubbles up or bubbles down to the top of the list in the first pass. Now, what is pass? I am going to explain it, but the problem with this bubble sort technique is this is actually less efficient technique in terms of time complexity. Its time complexity is actually huge, and therefore it cannot be used for the larger list. It can't be used because it is very less efficient. In order to understand the procedure of bubble sort, let us take an array of numbers which is 5, 1, 4, 2, 8, and we want to sort the array from lowest number to the greatest number, that is in increasing order. So, essentially what is happening? The list is 5, 1, 4 to 8. So, 5 and 1 are compared and swapped, as this is not the right increasing order. 1 will take the place of 5 and 5 will take the place of 1. Now, the array is 1, 5, 4, 2, 8. Now, again the second element and the third element will be compared, and if in wrong order they will be swapped. That means 5 and 4 both are swapped. Now, array is 1, 4, 5, 2, 8. Now, the comparison takes place between 5 and 2. So, it becomes 2 and 5 after swapping, since 5 is greater than 2, it was not in the correct order. So, 1, 4, 2, 5, 8, and now the comparison will take place between 5 and 8. So, 5 and 8 are there in the correct order. So, no swapping will take place here. So, here what happens? This whole 4 step is known as one pass, or it is known as the first pass. So, what happens at the end of the first part, which is a peculiar characteristics of the bubble sort technique, is the element 8, although it was already at the last place, but if it would not have been on the last place, it would have taken its place at the last. So, the last element, which is 8, is the largest element or the biggest element in the array. It has taken its own position. Coming to second pass of the technique, 1, 4, 2, 5, 8. So, now it will the comparison takes place between the elements, and no this thing takes place, no swapping takes place, as 1 and 4 are their own respective correct positions. Now, in the second iteration, I can say in the next iteration within that particular pass only, the comparison takes place between 4 and 2. So, now 4 and 2 not correct. So, it will be swapped. Now, it will be 1, 2, 4, 5, 8. That means elements are swapped because 4 is greater than 2. Now, coming to 1, 2, 4, 5, 8, which is the new array. 4 and 5 are swapped, no change. 4 and 5 are compared, no change, as they are okay. Then 5 and 8 are compared, no change, they are also okay. So, this is what you called second pass. So, at the end of the second pass, the element 5, which is the second last element in the array, has taken its appropriate position. Now coming to the third pass, 1 and 2 will be compared, no change. 2 and 4 will be compared, no change. 4 and 5 will be compared, no change. And then 5 and 8 will be compared, no change. Now in this third pass, no change has happened because the array was already sorted. It was sorted actually in the second pass itself, but the algorithm does not know that the array is sorted. So algorithm needs one whole pass which goes without any swap, because array was already sorted but algorithm was not aware of it. So this is a kind of, you can say, disadvantage. Even if your array is sorted, it does not require any swapping. Some extra passes will be taken by the algorithm. This will be taken care in the optimized version of the bubble sort technique. Coming to the pseudocode of the bubble sort, we are having one array and one the size we are passing it, which is integer n, and the upper it will be containing two loops. So one loop will go from 0 to n minus 1, that is for each and every element we need to compare the element it with the other, but the second pass will be going from 0 to n minus k minus 1. Now the important term here is n minus k minus 1, which is there to ignore the comparisons which have already been done in the earlier iterations. So first loop will go from k is equals to 0 to k less than n minus 1, and the second loop will go from I is equals to 0 to n minus I less than n minus k minus 1. In each and every loop we will keep on incrementing the I and k, and within the inner loop we will compare the two elements of the consecutive positions like ai and ai plus 1. So if ai is greater than ai plus 1, we need to do the whole swapping, and this will go for every element. So every element when compared, that means on completing one loop or one iteration for the complete inner loop, this is known as one pass, as I have already told you, and then it will be taking n minus 1 passes. So taking n minus 1 passes as shown in the example is actually a problem, because sometimes this n minus 1 passes are not required. So in order to optimize or in order to improve the bubble sort, we can put up a flag which will say that whether the swapping is happening or not. If the swapping within the inner loop is not happening, we will not go to execute the outer loop, or we will not go to execute the other iterations of the loop, and then we can break. So we can say for I is equals to 0 to loop minus 1, we will first of all insert a flag, which is, we can say flag is equals to false or swapped is equals to false. So within the inner loop, when we are swapping the items, we will set this flag true, and every time we keep on checking, every time before going into the outer loop we will check. If not swapped, then break. There is no need to go for the outer loop again. So in this way we can improve the bubble sort by removing the extra passes which are actually giving us nothing. Coming to the characteristics or the features of bubble sort, worst case and average case complexity of bubble sort is order n square. Worst case occurs when the array is in the reverse order what we are looking for, and the best case time complexity is order n. So best case occurs when array is already sorted. Sorting, whether it is an in-place sorting algorithm, yes, bubble sort is an in-place sorting algorithm, and bubble sort is stable also, but again as worst case and average case behavior or order n square, this is a less efficient technique of sorting. Coming to the next sorting techniques, which is insertion sort. So the idea behind insertion sort is we actually use this insertion sort in the normal routine course when we play cards. So when we play cards, what do? We take one card and arrange and fix it at the proper position, then we take another card and then fix it at the proper position, then we take the third card and fix it at the proper position. So this is what insertion sort is. So one element from the input list is taken in each iteration and we will be placing it in the correct position in the sorted array. So what is this sorted array? Sorted array initially is nothing. It's a blank list, or you may say it may contain only one element. It iterates the input elements by growing the sorted array by 1 at each iteration. In each iteration, the sorted array will be grown by 1. So we loop from I is equals to 1 to n minus 1. We'll pick the element ARR I and insert it into the sorted sequence 0 to I minus 1. So that means, let's say for an example, we have 3 sorted cards 0 to 3. We'll be taking the fourth card from the unsorted one and giving it its proper position in the sorted array. So initially my sorted array is not having any element. With each and every iteration it will grow by 1 element. So if it is the first element, then that means array is already sorted if it is an array of 1 element. If it is not, then we will pick next element, compare with all the elements in the sorted list, shift all the elements of the sorted list that are greater than the value to be sorted, insert the value at the proper position. So step number 4 and step number 5 are actually performing actually looking for the proper position of the card or the number in hand, and this will be repeated until the whole list is sorted. Let us understand this whole procedure by an example which is shown on screen. We have an array of 8 numbers 4, 3, 2, 10, 12, 1, 5 and 6. So essentially I don't have any sorted array. Now 4 comes into the sorted array. There is no element for comparison, so 4 takes at its own place. Now this 4 is actually my sorted array. I will be taking 3 in the next iteration and looking for the proper position of 3, which is before 4, and now 3 is inserted before 4. I will be taking 2, it is inserted before 3, then 10 is taken, 10 is at its proper position. So at this particular point of time, after 4 iteration, my sorted sub arrays 2, 3, 4 and 10. Then 12 is taken, 12 is also at its proper position. So the green marking is showing the sorted sub array. Then one element 1 is taken. Now 1, on comparing with the elements in the sorted sub array, finds its position as the first element of the array. So now it will be 1, 2, 3, 4, 10 and 12. Now we take 5. So it will be 1, 2, 3 and 5 will be inserted at its proper position, and then 6 is taken. So 6 will be inserted as at its proper position. So the array sorted will be 1, 2, 3, 4, 5, 6, 10, 11. So every time we are taking one element from the unsorted part of the array and inserting it at the proper position in the sorted sublist. But here we need to be very careful about that. We need to shift the elements in order to insert the element at its proper position. In case of 1, which is the 6th step here, we need to shift all the 5 elements to give 1 at its proper position. In case of 5 as the element, we need to shift 10 and 12, and in case of 6 again we need to shift 2 elements 10 and 12. So depending upon on which particular position you want to insert the element, you need to shift all other elements which are available on the right hand side of the array. So in order we will be performing this array this technique for all the elements. So the outer loop obviously will run from 0 till less than n or n minus 1 depending upon how you start indexing with. Then we need to store the current element whose left side is checked for its correct position. We will store this element into the an different temporary variable, let us say temp, and then we will check whether the adjacent element in the left side is greater than the current element or not. This will be checked by the condition while j greater than 0 and temp, which is your ai, the element in hand, temp is less than a j minus 1. That means here now we start, if this condition satisfies, we start moving the left side elements to one position forward by aj equals to aj minus 1, and then we will decrement the loop by j is equals to j minus 1, and then we will fix the current element to its correct position, which is the current element was stored in temp, we have earlier stored it, and then temp will be stored at the position aj. So by these two lines, which is aj is equals to aj minus 1 and j is equals to j minus 1, we are moving the elements to create a space for the element in hand to be inserted. Now insertion sort, it is an in place sort, it is a comparison based sort, as I have already told you in the beginning. It is an in place and stable sorting algorithm, but it is not suitable for large data sets as its average and worst complexity are of order n square, similar to that of bubble sort. Bubble sort is also having a worst case complexity and the average case complexity of order n square, which is considered as a high complexity. So the sorting technique is inefficient. Similarly here in insertion sort, it is the average and worst case complexity of order n square. Now where it is useful? It is more useful when array is almost sorted. When array is almost sorted, it will give you good complexity of order n kind of, and only few elements are misplaced in the complete big array, then it is the best way, or it is the best suitable sorting techniques to be called for if only few elements are misplaced in a complete big array. Coming to the next one, which is selection sort. Selection sort, as the name indicates, it will select the elements. It will select the minimum element from the unsorted list and it will keep it in the sorted list at the first position because it is the minimum element. Then it will discard that element from the unsorted list. With the remaining unsorted list, it will again perform the same procedure. It will look for the element which is minimum and place that element onto the second position in the sorted list. Now here I am talking about obviously the increasing order of the array. So basically it is also dividing, it is also based on the divide and conquer and incremental approach. It is dividing the array in a way into two lists, one is sorted, another one is unsorted list, and it is incremental in approach. Incremental in an approach, that means with each iteration it is growing up its sorted list. So basically what it is doing is, it is dividing the input list into two parts. One is sorted list that will grow from left to right, and the list which is remaining to be sorted. Initially the sorted sublist is empty obviously, and the unsorted sublist is the entire input list. We will keep on taking minimum elements and inserting those minimum elements into the sorted sublist. So take the minimum element and exchange it with the leftmost unsorted element, putting it into the sorted order and moving the sublist boundaries one element to the right for both the sublist. Coming to an example, let's have a look for the example of this selection sort. We have an unsorted sublist of numbers 11, 25, 12, 22, 64. The least element in the unsorted list is 11. Sorted sublist initially is empty, as you can see on the screen. We'll pick out the least element in the unsorted list, which is 11, and we have kept it into the sorted sublist. Now the unsorted sublist which is remaining is 25, 12, 22, 64, and the sorted sublist is being filled with one element, which is 11. Coming to the next step, in the unsorted sublist, again a least element will be taken off. So in order to take off the least element, we will run that process again, and now the least element in the unsorted list is 12. Now this 12 is added to the sorted sublist, making the sorted sublist increased by one position or by one element. Now the sorted sublist is 11 and 12, while this 12 is being discarded or being deleted, you can say, from the unsorted sublist. Now the unsorted sublist is having only 3 elements, which is 25, 22 and 64. So here you can observe that every time the unsorted sublist, with every iteration, unsorted sublist is shrinking. So the first or the starting boundary is moving to the right, and ultimately it is having no element, the unsorted sublist. And for the sorted sublist, the right side boundary is moving to the right side. So initially the sorted sublist was empty, and at the end it will having all the elements. Unsorted sublist will having the no element. So coming to the next iteration, the minimum element or the least element in the unsorted list is 22. Now this 22 is being added to the sorted sublist, making it 11, 12, 22, while the remaining unsorted sublist is 25, 64. Picking the minimum element which is in the unsorted sublist is 25, and adding it to the sorted sublist, making the sorted sublist as 11, 12, 22, 25. Now the last element in the unsorted sublist is 64. We will pick that 64 and add it to the sorted sublist, making the sorted sublist or the output as 11, 12, 22, 25, 64, and now sorted sublist is empty. So this was the whole logic behind selection sort. In order to perform it practically, in order to implement the selection sort, the pseudocode which we should have is, for j is equals to 1 to n minus 1, we will store the position of j, we will store the value of j in an element which is smallest, and now we will pick the position to be filled, which is j plus 1 to n. Every time we will be filling up one position by what? We will be filling up one position by a smallest. So a smallest is actually here. Now in the next two steps we will be finding minimum. We can say if a of I is less than a smallest, the value of I will be stored into the smallest. So every time, see, these two lines are here to find the minimum, and as and when we are able to find the minimum from unsorted list, we will exchange that a smallest with a j. That means the minimum element from the unsorted list has taken its own position in the sorted sublist, and that position is AJ. So, the outer loop is actually picking the position to be filled, and the inner loop is finding out the least or the minimum element from the sorted sublist, unsorted sublist. Coming to the characteristics of this selection sort. Selection sort is, yes, of course, it is an in place sort. It is not requiring the extra memory more than a particular limit, and but because of its worst case complexity being order n square, it is not suitable for the large list. So, whatever we have bubble sort, selection sort and insertion sort, both are not suitable for the large list because their worst complexity is order n square. But the difference between insertion sort, bubble sort versus selection sort lies in the stability. While the bubble sort and insertion sort are stable, your selection sort is not stable. It is going to change the order of similar value elements. Similar value elements, let us say there are two elements coming 4A and 4B. So, A and B are actually showing the position. Element 4 which is having 4A as its index is earlier, and the element 4 which is having B as its index is on the right side of the 4A, but this is a possibility in selection sort that in the output you will be having 4B first followed by 4A. That means this technique, this sorting technique is non-stable, while the insertion sort and bubble sort were stable. But yes, it is also an in-place sorting techniques, not suitable for the large list because of its worst case complexity. So, now in order to summarize what we have seen in this particular lecture is, first we have gone through searching techniques. What do you mean by searching technique? Is looking for a particular element. There can be various searching techniques, but for arrays there are two searching techniques. If we are using array as a data structure, it is having two searching techniques which are commonly used. One is linear search and binary search. The difference lies in the requirements as well as in the efficiency also. Linear search is not posing any requirement on the data values, while binary search will only work with the sorted data values. It will not work with the unsorted data values, and binary search is having its is actually more efficient because it is working on the approach of divide and conquer technique. It is dividing the element array every time by a factor of 2, while linear search is actually a sequential search comparing elements one by one. Then we have seen the meaning of sorting techniques. Sorting techniques are actually just a reordering of the input elements, and then we have seen three sorting techniques. One is bubble sort, insertion sort, selection sort. All these sorting techniques comes under the category of, I can say, inefficient searches because of their worst case and average case complexity. That comes to be n square for all the three sorting techniques. And yes, but with a bubble sort we can have one improved version of the technique which may improve the complexity or the running time up to some extent if there are not swapping, or there are no swapping required for the upcoming passes. Then we have seen insertion sort, again an inefficient sort which is yes, in place and stable. Bubble sort and insertion sort, both are actually in place and stable sorts, while the last sort which we have seen in this lecture was selection sort. So, selection sort is actually a non stable technique, it may change the order of the similar value elements also. So, these sorting techniques, although complexity wise are quite similar, but depending upon whether you want similar technique, whether you want stability or the stability is not a requirement, you can go for either bubble sort or insertion sort or selection sort. Also, insertion sort is very important when there are only you can say few mismatches or few misplaced elements within the array, then your insertion sort works well and it may give you a better time complexity. Thank you for patient hearing.